Another model that was used prior to Toyota business practices, and a lot of the people you'll see out in the world of consulting, for example, who work for Toyota, were really raised on the practical problem-solving model, which came before the Toyota business practices model. And it's really not very different in a way. Practical problem-solving is embedded within Toyota business practices. It doesn't have a specific step that says define the ideal state and break down the problem. So there are a few important differences, but by and large, the idea is similar. And you're starting off by clarifying the problem. When we initially see a problem, it's usually large and vague. For example, we have a lot of turnover in this plant, and we have to do something about turnover. Where is the turnover happening? Is turnover really a problem? Under what conditions is it a problem? None of those things are defined. We just know we have turnover, people are leaving, we have to stop them from leaving. So we start off by having just this vague perception that something hurts, there's some pain, and then we have to clarify that problem and, as I said, break it down until we finally have an actionable problem, and then we will start with the most likely root cause, and that may be root causes. So you may use, for example, the 7 quality tools and collect some data and do Pareto charts, and you may do a cause-effect diagram, and you're getting a picture of some of the causes, and then you're narrowing that down to the most likely causes. And part of that is finding out where the initial problem was seen, and then where the actual problem occurred. So you might see the problem in inspection, but then you have to go back through the process to find where it originated. And then you start to ask why. The first why is the direct cause. So if we have a customer complaint that their car stalled unexpectedly on a highway, then we know that we have a customer complaint, and that's the problem because we want 0 complaints. And then the direct cause is because the car stalled. At this point, that's all we know is that the car stalled, and that led to the complaint. We don't know that. We have to verify that, in fact, the car did stall and how it stalled. But then we have to ask why it stalled, and that may lead to a specific technical problem that caused it to stall. And then we have to ask why that technical problem occurred, and that may lead to something in the plant, like there was dust in the engine that should have been there. It may lead to a design issue in engineering, and the whys will take you wherever they take you until you get to what you think is the root cause. And again, the root cause is your best bet based on the data you have and your analysis and investigation. You're not certain that that's the root cause. But based on that root cause, you're going to identify some kind of countermeasures, try something, and then you're going to check, learn, further actions, share learning. So the point is that all of this is done with the mindset of a good scientist. Not every scientist is really good, but a good scientist who is skeptical, who wants facts and data, who doesn't believe that the actual problem is solved. You might be looking at some sort of new kind of fusion, and you might spend your whole life on this new kind of fusion, and you're solving a lot of little problems along the way, but you go to your deathbed saying, I never really solved the problem I wanted to solve. Still more work to be done. So there's actually documents that in Toyota that translated early documents from Ono's group that translate into discussing the scientific method. And a Toyota leader should always be following the scientific method. Part of the scientific method is you find why it happened, not who did it. This isn't a whodunit game. It's a scientific game of formulating and testing hypotheses. The process of getting to the root cause is really a narrowing process. For example, we have a problem that the car stalled, and there's many possible reasons why the car stalled, or did it really stall? Did the engine go off? Did it hesitate? Did it go off at a stoplight. Did it go off while the car was moving? And you have to find that out and define that more clearly. And then you can think of all the different reasons why it might have stalled, and that's why a cause and effect diagram is nicest, because it's a brainstorm of many different possibilities. Then you have to have some way of finding the most likely cause, and that may involve some even experimentation in trying different things to cause that particular car and that particular engine to stall. And then you need to find a point of cause, which is where did it actually originate? Did it originate in engineering? Did it originate in manufacturing? Did it originate in something the dealer did to prepare the car? Did it originate in something that the driver did that they shouldn't have done? Was it some sort of oil that they put in that they added after the fact that wasn't the right kind of oil? And through the 5 why process, you'll find the root cause. And then you are going to test that. I talked about defining the problem as being very important, and one of the problems with defining the problem is that you can come in at many different levels, and you might come in at the wrong level and then end up focusing on the wrong problem. So, for example, in this case, what the problem was seen as is reduced productivity. Productivity went down. And a good coach would ask you, okay, productivity went down. Why is that a problem? Or how do you know that's a problem you should be spending your time on? There's so many problems that any organization has, and you have limited problem-solving resources. So why are you going to focus on productivity? In this case, they asked the question, what happens when we have low productivity? And the answer is that our costs go up and we don't have good customer service, which are both important things. But we still ask further, right now, with where the business is, what are we strategically focusing on? In this particular case, they were strategically focusing on cost. So the real problem is that our costs are too high. And lower productivity is one source of high costs, and it's also one lever for reducing costs. But then I would also ask, what are other levers for reducing costs? Because it may be something that's much more important than productivity, for example, material costs. So that then if we discover that, in fact, productivity is a key driver and one that we want to focus on, then we can go backward and start looking at some of the causes of cost. And someone may initially say it's because people aren't working as hard as they used to. We've lost our work ethic in America, and they can go on and on about that. And then you would say that's one possible reason. Let's develop a cause and effect diagram with man, machine, method, material, and list all the possible causes, and then let's go out and pick the ones we think are most likely and collect some data. And that you collect data and you find scrap and rework is actually the biggest driver of reduced productivity because we're spending a lot of time fixing things. And really we should focus on quality, not in making people work harder. Okay, so the problem with a lot of what's done in the factories as problem solving is that, number one, we assume that what we initially see as the problem actually is the problem and don't really question whether that should be the problem we're working on. And number two, we often jump to a conclusion about the cause that's incorrect without thoroughly looking at other possibilities and going and seeing ourselves, going to the Gemba. The truth about PDCA is, and this is from the Total Field book, we have several chapters that go through the problem-solving process in quite a bit of detail. The plan always begins with problem definition, and it should define the ideal state versus the actual current condition, this gap, and that should be studied. The current condition should be studied at the Gemba, so we should understand in as complete a way as possible what's going on. In fact, it says you need to grasp the situation in a general sense before you even decide what problem to work on. So there has to be some general understanding of a lot of what's happening and the dynamics and the strengths of the people and the weaknesses of the process, and based on that general understanding, then you're going to then start to formulate ideas about what problems are important to work on, and you can define the ideal state versus the actual state. The gap is, with the ideal state, it would be like a grand theory in science, which is too big to actually test. So you'll hear about theoretical physicists that come up with breakthrough theories in quantum physics, and then there are experimental physicists who will then break that down into testable hypotheses and then they'll use their laboratories or equipment to run those tests. Okay, so you have to get from the grand theory to the smaller testable hypotheses. The small pieces then allow you to run small experiments with a great frequency, and therefore you're learning very quickly. If it's going to take me my lifetime to run one grand experiment, I get one chance, one shot at it. If I'm running an experiment every week, then I'm learning something every week that then informs what I do the next week, and there's hundreds of PDCA loops that are getting me closer and closer to testing that grand theory. For each of the pieces, for each of these small PDCAs, we want to go through the same PDCA process. What is the problem? What is the root cause? What is the countermeasure we're going to try now? What happened when we tried it? What is the next experiment we're going to run? As we're seeing countermeasures through, which is the doing part, there are in fact embedded PDCA loops. So in the case of that customer that had the stalling problem, we will try something, like it may be, we think a problem of the oil mix that was put in the car, so we'll try a variety of oil mixes, see if we can either cause the car to stall or not stall. And with each of those experiments we run, we're doing PDCA. And we're discovering which ones work and which ones don't work. So we're actually studying, analyzing, learning as we're in the do stage. What that means is that if you keep on checking, you'll see this in work groups in Toyota that have an annual goal. George mentioned Ocean Connery, which is an annual planning system. And everybody has an annual goal. And you may have a big, hairy, tough goal to reduce quality defects by 30%. And every week they're working on one defect they discovered, and they're doing a PDCA loop, and they're getting closer and closer to that tough goal. As they're eliminating those defects, they're doing PDCA and they're learning and they're charting that they're getting closer and closer to that 30% reduction. By the time they get to the check stage at the end of the year, they have checked many, many times, and really the only thing they have to do is the last check, the last week, say. So they pretty much know they're now sliding into home plate, and they know that they're making the goal before they actually get to the check stage. So the check stage actually becomes a more broad reflection on what happened this year, what we learned, and how it can prepare us for next year.